Hello, here is some feedback to the problem-solving question for the skills module in which we are looking at acids and bases. And I've just picked one of the questions at random. You probably noticed that every student got a different set of numbers, but the questions are all the same. So nobody got any disadvantage or advantage by having easier questions. That certainly is not the case. So in this video, I just want to quickly go through the calculations that you should have done so that you see at least the principle, although your numbers might be slightly different. I also want to point out that the program will tolerate a 10% deviation from the absolute correct value. So if the correct value is 100, the program will accept anything between 90 and 110 as correct. That means we don't really need to worry too much about whether you should have done 3 decimal points or 2 decimal points. It usually would not make any difference. So there are a couple of questions here. So in the first part, we are looking at acid and bases and calculate pH and pOH and maybe also pKb. And in the second part, we are looking at how we prepare a buffer for an experiment. So let's go to the first experiment. Where we say we have 289 milliliter of a 53.9 millimolar acid. And we note that there is no pKa given. So that means we are probably dealing with a strong acid. So no pKa given indicates strong acid. And we are asked to calculate what the pH and the pH of the solutions is. So we know that we have a strong acid, which means we can use the equation pH equals negative logarithm of the acid concentration, and the acid concentration is 53.9 times 10 to the minus 3. That is 53.9 millimolar. But we need to convert the milli into molar. That's why we've got the 10 to the minus 3, because the definition is that whatever is in this bracket of the log, and I should say it's log 10, but we know that anyway, that it has to be in molar. So the pH would be negative log of 53.9 times 10 to the minus 3 molar. And if we put that in a calculator, we get a pH of 1.268. I've given it as 3 decimal points, but 2 decimal points is absolutely fine. And as I said, it has a 10% error tolerance. We can also very easily calculate the pOH of the solution, because we know that the pOH is given as 14 minus the pH, which has calculated the pH. So we've got 14 minus 1.268, which gives us a pOH of 12.732. So that is the pOH of this solution. Now, the second question is, what is the pH of a 0.1 nanomolar hydrochloric acid solution? This is, it wasn't a sort of a trap or something like that, because we've discussed it in the lecture. But of course, we need to be careful. And if we say, for example, okay, we just simply apply negative log of the acid concentration for the pH, and we just simply put in negative log of 0.1 times 10 to the minus 9, which would be molar, we would get a pH of 10. But obviously this can't be correct, because we have a strong acid, HCl is a strong acid, and we would need a pH that is below 7, or at least 7 or something like that. But with a pH of 10, this would indicate that it's alkaline. So 10 cannot be the correct answer for it. So what we need to do is we can calculate the proton concentration here, and we have the acid proton concentration. That would be 1 times 10 to the minus 10 molar. And we need to also take into account the protons from the water, because we are so dilute that the protons from the water are taken into account, and that is 1 times 10 to the minus 7. That is the proton concentration of the water. And if we add these together, then we can put these proton concentration in here into our log equation, and we get pH equals negative log, of course that is to the base of 10, of the sum of the water and the acid protons, and that gives us roughly a pH just shy of 7. I think it is 6.9995 or so, which we would round up to 7. So in a way, it makes sense because the acid is so dilute, but it is still an acid, and we are in the range of 7 because it is so dilute. 10 would be absolutely wrong, because we can't turn an acid into an alkaline solution. Okay, so in the next question, we have been asked to use another pH calculation. So we've got a certain volume, but the volume actually doesn't play any role in it. It could be any volume, and because the volume does not go into the pH calculation. But what we know is we have a 214 millimolar acid, and we've been given a pKa of 6.5. Now we've got a pKa, which means we need to calculate, we need to treat the acid as a weak acid here. So if we've got a pKa, it means probably a weak acid. And in order for a weak acid calculation, we need to use this equation. This is an approximation, but it's a pretty good one. pH equals 1/2 of the pKa minus the logarithm of the acid. And of course, that's logarithm to the base of 10. So all we need to do is we need to put in our numbers. 1/2 of 6.5, that was the pKa, minus the log of 2.14 times 10 to the minus 3. We need to convert the millimolar into molar, because that is the convention for the pH. And if we calculate that, we get a pH of 3.585. Again, I've given it 3 decimal points, but the program has a 10% error margin. Now, with that, we can easily calculate the corresponding pOH, because we know that the pOH is 14 minus the pH, and we've just calculated the pH here. So that's 14 minus 3.585, and that would give us a pOH of 10.415. And for the pKb of the base, we know that there is this relationship of 14 minus the pKa. Now the pKa we have been given as 6.5, so our pKb would be 14 minus 6.5 equals 7.5. So this was basically the calculation for this question. Now we need to prepare a buffer, and we need to prepare 378 milliliter of the buffer, and we want to have a 311 millimolar buffer, which means that the total concentration of the acid and the conjugate base should be this 311 millimolar. And the pH of the buffer should be 5.7. So the pH is 5.7. The pKa of the acid is 6.1. And the first question is, we had a choice to figure out, do we need more acid or do we need more base? And we can say, since the pH of the buffer is 5.7, it should be smaller than the pKa. So the pH should be smaller than the pKa, which means that we need more acid. So more acid is definitely needed in order to fulfill this condition. pH should be smaller than pKa. So that's a very important bit of information that we have, and we then can basically look at our calculations later on and say, do we still have more acid in our calculations than base? Okay, so let's then calculate the ratio of the acid to base. So we can use the Henderson-Hasselbalch equation, where we've got pH equals pKa minus log of the acid concentration divided by the base concentration. We can rearrange this equation. We bring everything with a log to that side. The pH goes to that side. So we've got log of acid over base equals pKa minus pH. And we can put in these numbers. So 6.1 minus 5.7, that gives a difference of 0.4. So the acid to base relationship, the logarithm of the acid to base should be 0.4. And we can nicely get rid of then the log by just simply taking everything 10 to the power. So we get acid to base ratio equals 10 to the power of 0.4. And if we put that in a calculator, we get 2.512 over 1, or just simply 2.51, which we can write as 2.51 over 2. So that means we need 2.512 times more acid than we have base, which is in line with what we set up here. And if we want that for 100 particles of our base, then we just expand this fraction by 100 on each part. So we got 251.2 parts of acid per 100 parts of base. So that would be our ratio that we need for our buffer. Now, we need now to calculate how many millimoles of acid and base we need, but in order to do that, we calculate the number of moles in the buffer that we have, the total number of buffer moles. And we said that we want a 311 millimolar buffer. So 311 millimolar buffer. And we've got a volume of 378 milliliter. So 311 times 10 to the minus 3, that's the millimole per liter. That's our concentration. We've got the mole in the right place. Now we need to get rid of the liter. So we multiply that with our volume, which was 378 milliliter. And again, we've got the milliliter here. The liter cancel out, and all we need to do is put that into a calculator. And I just leave it not as mole, but I just leave it as millimole, which makes life a little bit easier later on. So we've got a total number of moles in the buffer of 117.558 millimole. And that is actually our acid and base mole together. This is the total amount of acid moles and base moles that should give us 117.558 millimole. We also know that the ratio of acid to base is 2.51 times. So we can just simply, very simply, sort of rearrange this equation that we have here and say that the acid is 2.51 times base. And now we just simply substitute this acid here that we have here with 2.51 times base. So we've got 2.51 base, that's our acid here, plus 1 base equals the total amount of moles, 117.558 millimoles. And we now have just one equation with one unknown. We can basically factor out the base. So we would have basically here 2.512 plus 1 base. When we factor out base, and that would give us in order to solve for base, we have 117.558, and I probably should put the unit here, millimole, and we divide by 3.512, that is this 2.512 plus 1, and we get for the base 33.47 millimole of the base. And for the acid, that's now pretty straightforward to calculate because the acid must be the difference between the base and the total amount of moles. So the acid would be 117.558. Of course, in millimole minus 33.47 in millimole, that gives us 84.08 millimole. And we see again, quite nicely, we need more acid than we need base, and that again is in line with what we've set up here. So it's always good to have a bit of a reality check. And so here we can put in the numbers into the spreadsheet. And again, here we've got because the pH is smaller than pKa, more acid than base is needed. So I hope this gives you an idea of what was expected in terms of calculations, and that you are happy with the way this assessment went. So thank you very much for watching.